Hello, welcome to a problem session. Today we're going to talk about damped harmonic oscillator. In the damped harmonic oscillator, we have a situation in which you remember a simple harmonic oscillator. In a simple harmonic oscillator, one dimension, we're going to look at one-dimensional simple harmonic oscillator. Model system looks like this. You have a spring attached here to some rigid wall, a spring constant K, and at this point let's say there's no friction, and at this point force on the mass is 0. So at this point F equal to 0, and at that point we place origin and call this x-axis. So at some other time this will be over here at some time t, and so this is x as a function of time t. So this is one dimensional because there's only one x I need to describe it. At that point force is in that direction, so x component of the force is minus k times x is positive at this point, but the force is pointed that way, so that's a minus comes from. And this system is our model, and there are other systems that we talked before. It's like a simple pendulum. If the angle is small, then this is also a simple harmonic oscillator. So these are like two systems, but we usually use this system to talk about simple harmonic motor concepts. So here, if you may remember, if the mass of this is m, so m d square x dt square, that's the acceleration, equals to minus k times x. So this is the equation of motion, and energy at any time is half m dx dt square, that's the velocity square, plus half kx square. So you can see that this is a function of time and this is a function of time, but turns out if you add them together, this is like independent of time. So energy here, when it's here it's the same, when it comes back over here and moves over there it's the same, when it turns around energy is same. So energy is same at every point. And so in this case, because energy doesn't go away, this will just go back and forth, back and forth. And if you think in terms of energy concept, then if you look at the potential energy is, this is the half kx square, and this is energy units. And if you let go at zero speed, from here, then so this is the x, so x equal to a and v equal to 0. You let go with this x-axis, then this object will move between here and there, just back and forth. You might think of this as a rolling in this well of potential energy. So this is a potential energy well, it as if a ball was rolling back and forth, but actually mass is, you can see that is like that, and this block is going back and forth on the x-axis. So that's a simple harmonic oscillator. Now so this is the background. You can see the solution for this was also x of t was some amplitude and some cosine, some omega t plus a phase. And A and phi depend on how I started, and this omega is the angular frequency with which this is going back and forth, is 2 pi over time period, and is related with k and m, or k and m here, square root of k over m. Okay, so this is a review of this undamped oscillator. So what is a damped harmonic oscillator? Well, a damped harmonic oscillator is, say we have this system, and you can think of that system even in that way, like this, back and forth, is swinging back and forth about the equilibrium. So this is undamped. Now suppose I wanted to damp it. Over here I can make this a friction surface, so it's going to damp. So that's one way to the damp system will be in this system we can make it friction surface. But this one, friction, kinetic friction depends on the speed. Kinetic friction actually is depends on the direction of the speed, but it's independent of the speed, right? So if I wanted to use your F kinetic friction from before, like a mu k n, and n will be a normal force, and this will be constant. So this would be a constant force, except that if this over here is going this way, if the v is that way, the fk will be that way. Over here it turns around. If v is that way, then fk will be that way. So the directional changing, and the math for that may be different. Okay, now say we think of this system that way, and maybe put this in a fluid, then there will be viscous force from the fluid, like air has viscous force. You can put in water or oil and things like that, right? So this force, the damping force here, F viscous force, is going to be proportional to, say we're going to use gamma v, and direction opposite to v. So this would be velocity. So if this is a x-axis, then if you write this guy, equation of motion, so it's going to look like that: m d square x dt square, that's the mass times solution, will have a minus kx about the equilibrium point. So the mg would be inside the minus kx at the equilibrium point, so I'm going to ignore mg, minus kx, and then we're going to have a damping force, which will be minus gamma dx dt. So it will be this equation, and this is the equation, that's the equation for damped harmonic oscillator we're going to talk about. If it's what will happen for this guy? Well, this guy will have m d square x dt square will be minus kx as before. Then you have plus f kx, and you have to write out equation for this situation and equation for that situation, and then when the velocity is going from here all the way here, we'll have one sign for this, and the velocity is going in the next half of the cycle, it will have another sign for this. So this sign can vary depending on which part of the cycle you're analyzing. And this captures, this is analytic, this particular situation gives us something that's analytic, and I don't have to worry about which part of the motion I'm in. So this is easier to deal with, mathematically. So when we study damped harmonic oscillator, we usually use this study. So let me erase this and look at this system a little bit more closely. Okay, look at the solution, look at the energy considerations. Here the energy will not be conserved, so let's look at it in the next slide. Okay, so we have a system where equation of motion looks like d square x dt square md square ct square equals minus kx. I'm going to call it minus b dx dt. I used a different symbol earlier, and I'm going to change to this more standard symbol now, and divide throughout by m. So it's going to be d square x dt square will be minus k over m x minus b over m dx dt. So you can see there were three constants here, k, b, and m, and now this is a combined constant, one constant and two constant. So the x depends on two parameters. So parameters k over m, we have encountered that before. We're going to call that, define that omega 0 square. And then there are b over m, we're going to call that gamma over, just gamma. We can just call it gamma, right? Or you used gamma earlier, but we're just going to call this gamma. Okay, and it's called damping parameter. Often you find sometime that this is also called 2 beta. You notice that gamma over 2, when you solve problems, appears a lot. So might as well define gamma over 2 as another symbol beta. But I'm not going to use that, okay? So this just becomes minus omega naught square x minus gamma dx dt. Okay, so this what are the solutions of this? Now this is a differential equation, which is when we had just this and this terms, it was easier to do, but over here it's much harder to do. So actually there are three types of solutions possible. Okay, 3 types of solution possible. So there are three types of solution, and here is the picture of the solution. So this is the like x of t on this side and the t this side. So one solution is like this, which is a oscillation, but amplitude keeps dropping with time. Another kind of solution is this kind of very quickly damps out. It really makes almost no, it doesn't make any oscillation. And another one not making any oscillation is this kind. But it damps out over a longer period of time. So this is called over damped, and this one is critically damped, and this one is called under damped. And you can see mathematical form with different, right? So it turns out those three cases is based on the relative values of this. If omega naught, you can see the units of omega naught is the same as gamma. See, the unit of omega, this is 1 over time square, right? Time square. And so this one is times x, as this is x times or divided by 1 time, and so gamma is 1 over time. So omega naught is 1 over time and gamma is 1 over time. So we can compare these two because they're same units. So if omega naught is greater than gamma, so that's one case, and another case is omega naught equals to gamma, and third case is omega naught is less than gamma. So gamma is actually you would say gamma, but it would be gamma over 2, gamma over 2, gamma over 2. That's what I was talking about earlier about beta. So these are the three cases. This is the case for underdamped. So this is actually the oscillator. This is the damped oscillator, which means it oscillates but damped, and this one is critically damped. So that's this case, and the third one is the overdamped. You can see that this side is the damping part is bigger than oscillating oscillating side. Okay, so we will do this because this is the oscillating situation, and in that case I'll give you what the x of t looks like. X of t looks like a cosine, but some new frequency, not omega 0, but some new frequency, omega, so let's omega 1 t. So it's gonna oscillate plus some phi. So it's just like this part is as if this whole thing was going with the same is oscillating. So this will be like oscillating without damping. Then if I multiplied this by e to the power minus gamma over 2t, so instead of that, the end result will be like that. So it's going to oscillate and die down. Okay, so that's this is damping, and so the amplitude is this part. So this is the time dependent or decreasing amplitude, and this is the angular frequency. So if this was from here to here is one cycle, then so this will be related with that cycle. Omega 1 will be 2 pi over cycle t1, and it is when you work out with this equation, this turns out to be square root of omega naught square minus gamma square over 4. So that's something that you have to see it. Where can you see all of these derivations? You can see all of this derivation in this website, that physics bootcamp. You can check that out. Don't forget to like this video also if you getting something from this descriptions. Let's now talk about the energy that happens, how the energy gets lost, and how as this thing is damping down, what happens to the energy of the oscillator. Okay, so we look at energy now. So in terms of energy, you know, energy is equal to kinetic energy plus potential energy. This is always the case, right? So even here, So kinetic energy is half mv square, and potential energy here, this is a system in which we have this is the system with a spring constant k. So potential energy here is only stored in this, and because the gravity is balanced out, so we not including gravity part. So potential energy is stored in a spring. So that's what the potential energy to the force in the spring, right? So that's going to be just half kx square. So this will not participate in potential energy because that force is non-conservative. It's a non-conservative, comes from non-conservative force BVV. That was the force. So there will be no potential energy with that. So this is energy. So if I if you look at energy at any time, t will be half dx dt, whatever the time is, square, plus half kxt square. And you can see we already have x, so you can imagine doing dx dt here, and nasty thing, you can write expression here and put in here. So you're going to get a very complicated, so this will give me a complicated expression, and it really doesn't do us any good to carry out this calculation. You can carry out, okay. A better system is unlike this thing, which is goes and couple of times is damps out. We are mostly interested, most times we are interested in what you call weakly damped. Means you will have this guy can go many cycles before it damps down, okay. So in this case, gamma is actually much less than omega 0. Not just little bit, much less than omega 0. So you can look at omega 1, for instance. So omega 1 will be square root of omega 0 square minus gamma square over 4. This will actually be very close to omega 0. You can expand this. For instance, you can say omega 0 times 1 minus gamma square over 4 omega 0 square to the power half, and you can do Maclaurin expansion on this guy, and you have a 1 minus 1/8 gamma square over omega 0 square, and it's roughly just keeping one term, and that just gives you omega 0 minus 1/8 gamma square over omega 0. So if this is the case, then this term is very small compared to that, and you can just use this if you want to be more accurate about it. But in many situations, you can just replace your omega 1 with omega 0 in a lightly damped, okay. Okay, so in the lightly damped case, energy, when you work this out, energy at any time t will be equal to half k a square e to the power minus gamma t. This is you can get this by using this and dx over dt in kinetic energy plus potential energy. Okay, I'm not going to work out the whole calculation, but you can see that if this expression looks like this, then you can, this is just time independent, and it's to t equal to 0. So this is E of t is kind of like E of 0 e to the minus gamma t. This is gamma times t. Let me see, but a gamma t. Okay, so from here you can actually see that dE dt equals to minus gamma e. And it's a pretty useful formula. All of this comes from all approximation, you know, but this is a, for lightly damped oscillator, this is a very important formula because we can do a lot. We don't have to kind of remember the answer. You just remember in terms of the rate of change of energy. Okay, it kind of tells how fast energy is dropping. It's pretty interesting to look at what this with time looks like. So suppose at t equals 0 you had this much energy, and so it says kind of the energy is exponentially dying, you know. This, it says this is at E at 0 time, and this is energy at any time t. So because something exponentially dying, this 1 over gamma is a very important thing, right? So E is 2.7 etc. So roughly 3. So if you look at this is 1 over E of E0. So the time it will take is 1 over gamma to actually energy to decrease to about 1/3 of it was. So this is a kind of characteristic time. So this is a characteristic time for this oscillator. So an oscillator will lose about 2/3 of energy in this much time. So it is saying that oscillator will lose around, so this is around 2/3, and only 1/3 is left, and this is about 1/3 is left. So lose about 2/3 of its energy in time 1 over gamma. So often this is a this question is asked that concerns how much energy you lose in how much time. So if you wanted to say how much energy in how much time to lose say 90% of the energy, so you just use this formula to get that. So you have a you're only going to be left with 0.1 E of 0, and you want to know how much time that is. So e to the minus gamma t. So you have to solve for t. How do you solve for t? Well, of course, E0 cancels out. You just take a log on both sides. So to solve for t, all you have to do is take a log on both sides. And so it'll be log of 0.1, natural log, minus gamma t. And you can see right away t that would require for 90% to go away will be, this will become 10 to the power minus 1. So this is actually negative. So log base e of 10 over gamma. So that's how you solve problems where this thing is used. So next I'll take about 5 to 10 minutes to talk about Q factor, which is also characterizes how quickly the energy is lost. Okay, this is one way to talk about how energy is lost and how quickly the energy is lost in a lightly damped oscillator. And there's another way which is called a Q factor. So Q factor is a important way to describe how quickly energy is lost. So there's a definition that we use. Q by definition is a denominator will be energy lost in one like a time, if you have one you go 1 radian, so in 1 radian cycle, 1 radian of cycle. So if you think of a cycle is 2 pi, so cycle is 2 pi, then this will be 1 radian, which is around, cycle is 2 pi, then this is 1 radian is about 60 degrees. So this is a and a starting energy. So whatever energy you have, and in the next 1 radian of a cycle, how much energy got lost. So if you lose a lot of energy in this, which means your oscillator is not very good, it's not oscillating, it's just damping out. So the smaller the denominator, meaning you're not losing as much energy in a fixed amount of cycle, which can compare different oscillators, but we can compare same amount of cycle for each oscillator. Each oscillator is going to have a different cycle time, right? So we need a measure to compare one oscillator versus another oscillator. And this gives us a unified way of comparing oscillators whose frequencies change. So we can just think in terms of a kind of reference amount of cycle, and we say 1 radian of a cycle rather than 2 pi radian is a cycle. We're going to just look at we could have said a quarter cycle or 1/6 of a cycle, something like that. So this is comes out like nicely because it's connected to 2 pi, and you'll see the formula turn out nicely when we use this definition rather than say, okay, per cycle or per quarter cycle or per half cycle. So this is a standardized definition. So smaller the denominator, better the oscillator, right? If we look at 2 oscillators start with same amount of energy, what fraction of energy got lost? Divide by that. So you can see I can very easily use this formula in here, and say starting energy is E0. Okay, I start with the E0, and then at the beginning of the cycle you have E0, and I go 1 radian of the cycle. So the time is you have a t for a full cycle, which is 2 pi over omega 1, and so I want not the full cycle, but 1 over 1 radian, the time. So the time we want is going to be divided by 2 pi. So I want is 1 over omega 1, and so this is going to be E0 e to the minus gamma over omega 1, and of course the E0 kind of cancel out with everybody, and for lightly damped it's going to be 1 over 1 minus gamma over omega 1, and this is going to be, I'm going to do absolute value, so kill the negative sign there, minus 1, and 1 cancels out, and so it's omega 1 over gamma, but this is very close to omega 0 over gamma. So sometimes people use omega 1 over gamma, sometimes people use omega 0 over gamma. So let's look at a couple of numerical examples of application of the Q formula. Okay, let's look at this simple illustrative problem for use of Q. So it's really not given just using the formula Q, but there's a description that the frequency was this, and then 90% of this loses in 2 seconds. So it's actually both of these formulas you will need to use. This thing is giving us omega 1 or omega 0. So it's giving us this part, and this part is given by description of energy loss. So take a ratio and given time, so get gamma, right? So it loses 90%, only 10% is remaining. So 0.1 is 0.1 E, let's call E0, and had some beginning energy. E0 minus gamma times 2 seconds times 2. So this I have to solve for gamma. So to solve for gamma, you can see this is minus log 10 is equal to minus gamma 2, gamma times 2. So gamma equals to log 10 over 2. So that's the gamma. And the frequency omega 1 will be this in the frequencies in hertz. So it's going to be 2 pi times 1,000 per second. So that's the omega 1. I can take a ratio to get the Q, and the Q will be just 2 pi times 1,000, and this was in seconds, so this is per second. So both of them per second, and log 10 over 2 per second. So these per seconds are cancelled out, and so you have a 4 pi over log 10 times 1,000. So you can use a calculator and get answer roughly for what the Q value will be. Okay, so I'm going to stop here. Next thing I'm going to discuss is a driven damped oscillator, and there we're going to talk about resonance. Okay, so that's it for now. Okay, bye.